Okay, let's solve this problem. We have an ideal gas in a piston cylinder device. And this one undergoes an isothermal compression process. So temperature T remains constant. And we know the initial pressure and volume. So P1 is 100 kilopascal. V1 is 0.6 cubic meters. And there is a heat transfer of 60 kilojoule from the ideal gas to the surroundings. Determine the volume and pressure at the end of this process. Okay, so we have Q out. That is 60 kilojoule. So let's solve this problem. So we can use the energy balance equation. The energy balance equation is Q in plus W in minus Q out minus W out mass times U2 minus U1 plus moving boundary work. So this is the energy balance equation. Now we can evaluate one by one. We have a heat transfer from the system to the surroundings. So we have Q out. That means the system is at a higher temperature than its surroundings. Because of the second law of thermodynamics, heat transfers from high temperature to low temperature. When there's a heat transfer from the system to the surroundings, that means the system is at higher temperature than the surroundings. Therefore, there is no heat transfer to the system. So you can neglect Q in. There is no information about W in or W out, so you can neglect them. Then how can we determine U2 minus U1? We can use specific heat. So there are two different ways to determine this U2 minus U1. If you have phase change materials such as water, refrigerants, R134A, we need to use a table to evaluate U1 and U2 after determining their phase change processes. But if you have an ideal gas, which is a pure system, then we can use specific heat. Then if you don't remember, the way to use the specific heat is simple. H2 minus H1 is Cp, T2 minus T1. So there's a specific heat Cp. And U2 minus U1 is Cv, T2 minus T1. So there is another specific heat. So Cv. So we can use either Cp or Cv. How do we determine Cp and Cv? From this table A20. So if you go to table A20, you can see specific heat values at different temperatures. Okay. Then in this energy balance equation, we need to determine U2 minus U1. So we can replace U2 minus U1 with Cv T2 minus T1. So here, mass times specific heat Cv T2 minus T1. That's how you determine a change in the internal energy of the system. What about WB? WB. There are 5 different ways to determine this WB. And we have an isothermal process. Just for your information, WB can be determined by these 5 different ways. The first one is when we have constant volume process, then WB is 0 because there is no moving boundary since volume is constant. And the second process is constant pressure process. In this case, WB is pressure times V2 minus V1. The third one is when you have constant temperature process, which is this one, isothermal process. WB is pressure times volume, natural log V2 over V1. And if we have a polytropic process, PV to the power n is constant, then WB is P2 V2 minus P1 V1 over 1 minus n. And finally, we can use PV diagram to determine moving boundary work by calculating the area. So in this case, we have an isothermal process. So this is how we determine moving boundary work. P V natural log V2 over V1. So now we are ready to solve this problem. This Q out is 60 kilojoule. So this one is 60 kilojoule. And T2 and T1, they are the same because it's an isothermal process. So this whole thing goes away. And so 60 kilojoule is PV natural log V2 over V1. Then minus 60 kilojoule is pressure times volume times natural log V2 over V1. And we can say this one is P1 V1 or P2 V2 because P times V should be constant when you have an isothermal process. And we know P1 V1, P1 is 100 kilopascal. V1 is 0.6 cubic meters. This one is 0.6 cubic meters. So we can determine V2. So from this equation, V2 is 0.221 cubic meters. What about the final pressure? When you have an isothermal process, pressure times volume is constant when temperature T is constant. Why is that? If you think about the ideal gas equation, PV is mRT, then since we have a closed system, mass is constant, R is gas constant, which is constant. Temperature T, this is an isothermal process, so temperature is constant. So pressure times volume should be always constant. So we can say P1 V1 is the same as P2 V2 because that is a constant. P1 is 100 kilopascal. V1 is 0.6 cubic meters. V2, we just calculated 0.221 cubic meters. So you can determine the pressure at the final state. So P2 is 272 kilopascal. That's how you solve this problem. Any question? No? Okay. Am I going too fast, too slow? Good? Okay. Are you all enjoying, are you all expecting the fall break? Yeah. I will be gone somewhere. I will leave tomorrow, 6 a.m. Yeah, with another family. My son's friend's family. We go to downtown Chicago. Staying there for 3 nights. It's so expensive. No, so expensive. That's so. Parking is $80 in the hotel. The hotel is crazy. The funny thing is that there are the regular price is pretty high, but if you find a deal, it goes down. So we are staying the one of the downtown hotel, and for 2 nights for the 2 families, the regular price was $2,000, excluding parking. That is even worse, right? Yeah. So I went to Priceline. There was a express deal or something, and it doesn't show the name of the hotel, but it shows some clues, like that there are total reviews of this unknown hotel is 8,000 something, and the guest review score is about this number. So I'm matching this, and I found, okay, so this one is $500 hotel, which is only $150. So I called my friends, my son's friends, the father. I think we need to, the risk. We need to take some risk, because I think 90% chance this is the right one. And everyone, they gathered together a few days ago in my house, and we pressed the button. Yeah, that was the right button. Awesome. Yeah. That's definitely a lot. Yeah, that was fun. That was fun. 500 per room per night went down to 150. Yeah. But there was a catch, So there's a resort fee, and there's a tax, and another fee. There are so many fees adding up, and then it ended up about $300 per night. Yeah, but still cheaper, but that was double. Yeah, not 150. Yeah. And then my friends found another deal, which is he has a membership in the museum in Midland. There is a museum in Dow Museum, for the Center for the Art and the Science. So he has a membership there, and then when you have a membership there, you can visit other museums in the same association for free. That I didn't know that. But there's a limitation. So you need to travel at least 90 miles. So there's a home museum, and within 90 miles, they are not free. But if you go outside, then it's free. Yeah. If you go to Chicago, that is beyond 90 miles. So we booked the 3 museums. Each cost about $30 or $40 per person. They're all free. That I didn't know that. Okay. So we are going. Previously, we studied a pure gas system. So we are going to study solids and liquids. So there's nothing different. The only difference is that previously, to use specific heat, these are the equations. H2 minus H1 is Cp times T2 minus T1. And for U2 minus U1, it is Cv T2 minus T1. But the difference between H and U is the definition of H is U plus PV. Then, what if we have a solid or a liquid? What is the main difference between gases and these solids and liquids? Gases are compressible. Liquids and solids are not compressible, right? No? So if you have a gas, you heat it, its volume goes up, right? If you cool it down, the volume goes down. But if you have a liquids and solids, the volumes are constant. In reality, there is a change in their volumes. However, the change is small, so we assume that they are practically constant. They are, in other words, incompressible. So when there's no volumetric change, this second term in this equation goes away. So the change in enthalpy is the same as the change in internal energy. So what is the difference between these two? Nothing. So when you have a solid or liquid, there is only one specific heat. Just C, because they are the same. H, U are the same, right? So the conclusion is when you have a solids and liquids, there is only one specific heat. However, when you go to the field, you will see people, saying this one is a CP, even though there is only one C. It's just CP is more common than CV, so people just call this one CP. But that doesn't mean that there's a CP and CV. In solids or liquids, there's only one specific heat for solids and liquids. Okay? So that's all. So based on this information, let's solve this problem. Consider a 1000 watt iron whose base plate is made of 0.5 centimeter thick aluminum alloy. And we know the density of this alloy and the specific heat. The base plate has a surface area of 0.03 square meter. Initially, the ion is in thermal equilibrium with the ambient air at 22 degrees Celsius, assuming 90% of the heat generated in the resistance wires is transferred to the plate, determine the minimum time needed for the plate temperature to reach 200 degrees Celsius. So what we need to do first, we need to determine our system. So what is our system? Resistance wire, or the whole iron, or the base plate, or the air surrounded? How do we determine our system? When we determine a system in a thermodynamic problem, you need to look at what properties is changing and whose property is that. So what property is changing here? What is the main property? Density? No. Specific heat? No. What is changing? Temperature. So temperature is the property of interest. Whose temperature is changing? The base plate. The base plate. So the base plate is our system, this one, and the temperature of this base plate is going to increase from, where is the initial temperature? The ion is in thermal equilibrium with the ambient air at 22 degrees Celsius. It means the ion is at 22 degrees Celsius. So the initial temperature of the ion is 22 degrees Celsius. The final temperature of the ion is going to be 200 degrees Celsius. So T1 is 22, and we have a heating process. So T2 is going to be 200 degrees Celsius. Then, to increase this temperature of this ion, we need to provide heat. So where is the source of the heat? It says 1000 watt ion. What does it mean? Benzene? No. It means this ion is going to consume 1000 joule per second. So when you use it for 10 seconds, it means that you just consumed 10,000 joule. Then, is that the heat transfer? So there's a heat transfer into the system, Q in, that is 1000 watts. Is this right or wrong? So there are only two choices. 50% chance to be right. Not multi-selected, right? Just two. So is it right or wrong? Wrong, yes, right. Then why it is wrong? Why it is wrong? Yes, it should be joule. So this, then what is 1000 watts? Power. In terms of heat, the rate of heat transfer, not the heat transfer. So how can you determine the heat transfer? Multiply by how long? Time t, delta t. So that is the heat transfer. And it says only 90% of the heat generated in the resistance wires is transferred to the plate. So 10% is lost to the air. So not 1000, it's going to be 900 watt. 900 watt times T is heat transfer Q. So that's it. So we have a heat transfer. There is a temperature increase from 22 degrees Celsius to 200 degrees Celsius. Now we have a thermodynamics problem. So what you need to do? What we need to do? We need to write the only equation that we know, the energy balance equation. So the energy balance equation is Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. So let's evaluate each term one by one. So we have a heat transfer in. So the resistance wire is heating the base plate. And what is the heat transfer? 900 watt times delta T. And we don't know how long. What about energy transfer by work? There's no energy transfer by work. Heat transfer, you can neglect them. So you can neglect all of them. What about moving boundary work? The base plate, the volume is constant. So there is no moving boundary. So you can neglect WB. So what do you have? Mass times U2 minus U1. Then how can you determine U2 minus U1? Using specific heat. C, T2 minus T1. So this is mass times C, specific heat, T2 minus T1. But many people just, they like to say CP. So don't get confused. Then, what is the initial temperature? 22 degrees Celsius. What is the final temperature? 200 degrees Celsius. What is the mass of the system? Do we have the mass of the system? No, but we know the density. Why the density is given? Because we can determine the volume and multiply by this density will give us the mass of the system. Because mass is density times volume. Then what is the density? 2770. 2770 kilogram per cubic meters. Then what is the volume? We have the thickness of this base plate, 0.5 centimeters. You don't like centimeters, you like meters, right? 0.005 meter times, do we know the surface area? Yes, 0.03. 0.03 square meter. So we have everything. What about specific heat is given? 874. 874 joule per kilogram degree C. So we have everything. Can you determine how long it takes? Now, yes. Where is it? So we need 72 seconds. 71.9 seconds is needed to raise the temperature of this ion to 200 degrees Celsius. Any question about this problem? Not difficult, right? So if I give you this problem in your second exam, can you solve it? Yes, you can, right? One more problem, then that's all for chapter 3. Then you can have our next homework assignment due by a week from today. If you need a break, for the full break, I can extend the due date the following Tuesday. Yeah. Yes. If all one. Okay. Okay. Everyone is okay, right? Okay. Having a due date. All right. The last problem. We have an electronic device dissipating 25 watts, has a mass of 20 grams, and a specific heat of 850 joule per kilogram degree Celsius. The device is lightly used, and it is on for 5 minutes and then turned off for several hours, during which it cools to the ambient temperature of 25 degrees Celsius. So the initial temperature is 25 degrees Celsius. It's going to be turned on for 5 minutes. Determine the highest possible temperature of the device at the end of 5-minute operating period. Okay, so we have this electronic device whose mass is pretty small, 20 grams, but you don't like grams. 1,000 grams is 1 kilogram, so 0.02 kilograms. Always use the same unit in your energy balance equation. Do not mix them and then make a mistake in the unit conversion. And it dissipating 25 watts. So where this 25 watt is going to be used? It's going to heat the electronic device, right? So the heat transfer goes into this electronic device by its own, the chip inside, that is 25 watts. So Q in is 25 watts. Am I right? It's a silly question because we just had, had the same in the previous problem. You need to multiply by delta T. And how long? 5 minutes. So 5 minutes, you don't like minute, right? So you need to converted to second, 60 seconds per minute. So it's going to be 300 seconds. Determine the highest possible temperature. Why does it say the highest possible temperature, not the temperature at the end? Because when you heat it, there will be, the heat loss to the surrounding. So when is the highest possible temperature? When we, minimized the heat loss from the electronic devices. So our assumption is that to determine the highest possible temperature is going to be there is no heat loss. Then we will get the highest possible temperature. In reality, the actual, the final temperature will be less than the highest possible temperature because of the, the heat loss to the surroundings. So now we have a heat transfer input, we have the mass, we have the specific heat 850. So we are ready to solve this problem. Okay, let's do that. So how can we solve this problem? There is only one equation that we studied in thermodynamics. That is the energy balance equation. Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. And what kind of heat transfer? We have 25 watt times 300 seconds. Do we have energy transfer by work? No. So you can neglect them, neglect them, neglect them. What about moving boundary work? There's no moving boundary work because our system is a solid. Then we have mass times U2 minus U1. How do you determine that? Mass times specific heat. Specific heat, C, just C, but the people like to say CP, times T2 minus T1. Then what is the mass? 0.02 kilograms. What is the specific heat? 850 joule per kilogram degree C. What is the initial temperature? 25 degrees Celsius. So what is the final temperature? If you do the calculation, you get 466 degrees Celsius. Any question? Is there any problem here? There is a problem. So the electronic device temperature is going to go up to 466. So what's going to happen? Well, you need to buy another new electronic device after using this one, because the electronic device cannot survive at this temperature, right? So what is the solution? Of course, you can, innovate that electronic device that will dissipate less amount of heat, but it's gonna take a lot of time. So thermodynamically, what we can do is we can add a heat sink. What is a heat sink? Another mass surrounding this electronic device that is going to share the amount of heat transfer heating this electronic device. So this much heat, 25 watt times 300 seconds, is not only going to be used to heat this electronic device, but the whole thing. So you just need to, attach a big mass so that you can lower the final temperature. So this time we are going to add 0.5 kilograms of aluminum block on top of this electronic device. So let's solve this problem. Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1. But this time we have not only the electronic device, but also the aluminum block. So two masses. So you can write this twice. Mass of the electronic device, U2 minus U1, plus mass of aluminum block, U2 minus U1, plus moving boundary work. And we all know there is no moving boundary because our system is a solid. The rate of heat transfer, not the rate of heat transfer, the amount of heat transfer is 25 watt times 300 seconds. And what is the mass of the electronic device? 0.02 kilogram. What is the mass of aluminum block? 0.5 kilogram. How do you determine U2 minus U1? By using specific heat. Cp, T2 minus T1. Cp, T2 minus T1. What is the Cp of electronic device? 850 joule per kilogram Celsius. And what is the initial temperature? 25 degrees Celsius. What is the specific heat of aluminum block? If you go to table 19, A19, aluminum specific heat is 0.903. That is kilojoule per kilogram Kelvin. So if you only want to use joule, it's going to be 903 joule per kilogram degrees Celsius. The initial temperature, again, 25 degrees Celsius. Now we only have one unknown, T2, they are the same thing. Now you can determine the final temperature of this electronic device, only 41 degrees Celsius. So, okay, so this one should work, right? Much lower temperature. Of course, when you design an electronic device, of course, you can, accelerate the heat loss, trying to make it, the efficient electronic device. Like, like for example, when NVIDIA trying to make this GPU, the previous one, the H1, they use an air cooling system. Now the second one, the Blackwell, you're not aware, they use a liquid cooling system. So trying to increase the rate of heat transfer, or you can add this heat sink, which can be much simpler solutions to minimize the temperature rise. One example you can see this one is sometimes let's say that you are trying to have a boiled egg. How are we going to do that? So there is water in a pan, the water up to this much, and there are eggs inside, and then you heat it, right? Maybe after 10 minutes after, then you take this one out and then you eat it. Can you eat it? No, because of the shell, you cannot eat it. So you need to remove the shell. Can you do that? Too hot, right? No? So if it is too hot, what do? You cool it down, or you can wet your hand and then touch it. No? No idea. When you need to, to touch something is hot, what do you want to do? If you need to, to grab something which is hot, you can touch water first and then grab it. Why we do that? You don't do that? No? Okay. So sometimes, when you go to a circus, when you go watch a circus, there are people trying to, play with, the fire, right? And then they touch fire, but they don't get burned. Why is that? They have an oil, covering their hands. What does it mean? The oil is working as a heat sink. So the temperature rise inside the fire is limited due to the, the liquid surrounding their hands, so they don't get burned. That's a heat sink. Okay. I need to find a good example for this one. Sometimes, you see people trying to put fire into their mouth, like, when you go to circus. How they do that? They drink water, or they drink, there's some kind of, oil inside, trying to, add more, the his things. That's another good example, right? I need to find something. Okay, so that's everything about chapter 3. So we have a new homework assignment, which is going to be due by not a week from today, the Tuesday after next week. We have 30 minutes, so let's talk about chapter 4. Mass and energy of control volume analysis. Control volume analysis is for an open system. So previous chapter 3 was for control mass analysis. Control mass analysis means closed system. Control volume analysis means open system. What is the difference? Control mass analysis means that mass is constant. So that's the definition of closed system. The closed system does not necessarily mean that something is closed. It means mass is constant. When you have an open system, such as this kind of system, so there is inlet, there is an exit. So let's say that water is flowing in this pipe and chamber, and there's a mass goes into this system and mass leaves the system. So what is the mass of the system? Can you determine the mass of the system when you have a continuous, the mass flow? You can't. So instead of studying, instead of, assuming constant mass, when you have an open system, when you have an inlet or an exit, we only study a volume. So this is the volume that we are going to analyze. That is control volume analysis, which is an open system. Then, how can we study this open system? We have mass transfer. That is different from the previous chapter 3. So, the first thing we need to study is mass transfer in and mass transfer out. So when we study mass transfer, it is convenient to use flow rate. Instead of mass, we can use mass flow rate. Instead of volume, we can use a volume flow rate. Because when you have a steady open system, we have a continuous, the mass is entering the chamber continuously. So we cannot quantify how much, the mass entered this system. What about if it is continuously working, like an air conditioning system? How much mass in the air conditioning system? We cannot say, right? Because we do not know. But if you study the mass flow rate, the mass flow rate is going to be constant. So we may know that. So instead of mass, we like to use mass flow rate. And we already studied mass flow rate in chapter 2. How do we determine this mass flow rate? Mass flow rate is mass per time, and when you divide a property by time, you put a dot on top of it to show that this is the rate of this property, that is mass flow rate. There are two different ways to determine this mass flow rate. The first one is density times volumetric flow rate, and the other one is density times average velocity times cross-sectional area. So that's how we determine mass flow rate. Then let's study mass balance equation first. So when we have an open system like this, the mass goes in, so it's going to be not just mass, it's going to be mass flow rate, m dot at the inlet. So there is a mass leaving the control volume, which is m dot at the exit, m dot out. Then how can we use conservation of mass principle? Mass transfer goes into the system minus mass transfer leaving the system should be the change of mass of the system. That is the definition of conservation of mass. But when we study open system, most open systems are steady state. What about this air conditioning system? Is it steady state or unsteady state? If it is unsteady state, what is an example of unsteady state? So the temperature is going to be the key property of this air conditioning system. Unsteady air conditioning system means that the temperature of this classroom goes down from 20, maybe an hour later, it becomes 10 degrees Celsius. Tomorrow, 0 degrees Celsius. The next day, minus 20. And maybe next semester is going to be 0 Kelvin. Make sense? No. So when we study an open system, most open systems are steady state. What about when you drive a car? If your engine unsteady or steady? At the beginning, we say warming up, so that's unsteady. But once it reaches a certain temperature, it is steady state. You remember, that when you drive, that you have a couple of gauges. One of them shows, the CMH. So this one, initially, at this lowest temperature, when you drive, it goes up and it stops somewhere. Then you can say it's a steady state. What about it becomes unsteady? What happens? We need to buy a new car, right? So most open systems are steady state. No, you don't have to buy a new car. You can go into the engine room and then, or no. My first car went this month, so we sold it. It was a Jetta from Volkswagen. After that, I don't buy German cars anymore. Okay. Then how can we, use the mass balance equation? So when we have this kind of open system, we have mass transfer input, m dot at the inlet and m dot at the exit. So if we apply conservation of mass principle for this steady state open system, m dot at the inlet should be the same as m dot at the exit. So that is the mass balance equation. Whatever goes in should leave, right? If you eat 2 kilograms of hamburgers this morning, if you don't put 2 kilograms of, in the evening, then you get weight gain, right? That's not That's an unsteady system. So if you want to have steady body system, the mass of your eating should be the same as the mass you release. That's the mass balance equation in a very funny way, right? I think that's the nature of the nature of humanity. My son, 4-year-old, still like talking about poops, and now we are all grown up. Still, the smiling about the poop stories, right? Even when we go to 80 or 90, we still be the smiling about poop stories. No, no more poops anymore. Okay. Okay, so that is the mass balance equation. What about energy balance equation? How can we determine energy balance equation? So when we write the energy balance equation, we need to think about what kind of energy transfer we need to consider. The best way to understand the energy balance equation for this open system is to compare with the energy balance equation of a closed system. So there's a closed system. So how do we determine the energy balance equation? So we first need to think about energy transfer. What kind of energy transfer in this closed system? 2, heat, work, right? When we have a closed system. That's a closed system. So when we, write the energy balance equation, heat goes in plus energy transfer by work goes in minus heat transfer goes out minus energy transfer by work goes out is going to be the change of energy of a system. That is the energy balance equation for a closed system. What about open system? We may have heat transfer Q. We may have energy transfer by work W. What else? The energy of the mass entering the system, right? When you eat something, it has calories, right? That's energy, right? So we need to consider energy by the mass, energy by mass. And there is energy leaving the system by this mass, leaving the system, energy by mass. So there are 3 types of energy transfer: heat transfer Q, energy transfer by work W, energy transfer by mass E mass. Then the next question is, okay, I know how to use Q and W in an energy balance equation that we studied in chapter 3. Then how can we determine energy transfer by mass? It's nothing new. We use the same thing that we studied in chapter 2. When you want to determine this energy is going to be mass times lowercase e, total energy per unit mass. Then how do you determine this total energy per unit mass? Do you remember? Total energy per unit mass was specific internal energy U, kinetic energy velocity square over 2, and potential energy gravity times elevation Z. So that's how you determine energy transfer by mass. Then based on that, let's complete energy balance equation. So what is the concept of energy balance? Conservation of energy principle. Energy transfer into a system minus energy transfer out of a system should be the same as change of energy of a system, right? Then let's think about energy transfer into a system. First, we can consider energy transfer by heat Q. So Q in. Then we can consider energy transfer by work, W in. Okay, nothing new. The same as the previous chapter 3. Then now we have energy transfer by mass. How do you determine that? Mass times U plus kinetic energy plus potential energy. Mass entering the system, m dot at the inlet, this one has specific internal energy U at the inlet plus kinetic energy, specific kinetic energy, velocity square over 2 at the inlet plus potential energy at the inlet, gravity times elevation z at the inlet. Minus energy transfer out of a system. So what kind of energy transfer out can we consider? The same thing, heat transfer Q, energy transfer by work W, and the mass at the exit. Q out plus W out plus m dot at the exit, m out. This one has specific internal energy, U out plus specific kinetic energy, velocity out square over 2 plus potential energy, gravity times elevation z out. It's going to be the change of energy over system. How do you determine the change of energy over system? The total energy at the final state minus total energy at the initial state. How do you determine the total energy at the final state? Mass at the final state times specific total energy at the final state minus mass at the initial state times total energy at the initial state per unit mass. Then how do you determine total energy per unit mass? The same thing, U plus kinetic energy and potential energy at the final state. So mass at the final state times specific internal energy at the final state plus kinetic energy at the final state plus potential energy at the final state minus mass at the initial state. It has specific internal energy U1 plus specific kinetic energy V1 square over 2 plus specific potential energy, gravity times elevation Z1. So this is the energy balance equation for an open system. But that's not it. Let's talk about mass entering the system. You remember about the story that I told you that, that this class is so famous, so completely filled with students, and there is a new student wants to come in. Then what's going to happen? Let's assume that this door is the inlet of this, the open system. So if there is a mass entering the system, what does mass need to do? It's completely filled with mass. So if I want to enter this control volume, I need to push the mass standing at the door and then make my space and walk in, right? So if I want to do that, I need to provide work. What kind of work? Pressure to create my space times volume. So pressure times volume is the energy carried by the mass entering the system. Pressure P at the inlet times volume, but taking mass out, specific volume, E times V. What about mass leaving the system? When mass leaves at this, the exit, when I walk out, I'm going to, pull, the someone, the standing next to me to fill this, the space. So pressure times that space volume is going to be the energy carried by this mass leaving the system. Pressure P out times V out. So that is the energy balance equation. This is the energy balance equation for an open system. Open system. Oh, wait, we were talking about steady open system. This is the energy balance equation for an open system. Then how can we convert this energy balance equation for a steady state process? When it becomes steady state, what happens to the energy change of the system? The total energy at the final state, total energy at the initial state, they should be the same because it's a steady state system. There's nothing changed in time. So if we say this is a steady state, steady open system, you can neglect the total energy at the final state minus the total energy at the initial state because they are the same. And there's one more. You may remember this one, U plus PV. What is U plus PV? Do you remember any property whose definition is U plus PV? Yes, H, enthalpy. So these two together becomes H at the inlet. These two together becomes H at the exit. The last one, do you remember that, when we study steady open system, it is convenient to use flow rate rather than just mass. So we can use mass flow rate. So how can we have a mass flow rate? Divide each term by mass. Divide each term by mass. That means we can add a dot on top of each property. Then, since there's nothing on the right-hand side, can we move everything, the going out to the right-hand side? Yes, we can. Then the energy balance equation is going to be for steady state open system, Q dot in plus W dot in plus M dot at the inlet. This one has enthalpy, kinetic energy, and potential energy. Is Q dot out plus W dot out plus M dot at the exit. This one has enthalpy, kinetic energy, and potential energy. This is the energy balance equation for a steady state open system. So we are going to study this equation for many different devices, starting from nozzle, diffuser, turbine, compressor, valves, pipes, mixing chambers, and heat exchangers, and etc., etc. So that's everything. That's the theory that we need to study any thermodynamic devices in chapter 4. This one, energy balance equation and mass balance equation. Any question up to here? No? Okay. Then let's study our first example. Nozzle and diffuser. What is nozzle? Is a device, looks like this. We have a large opening at the inlet. We have a small opening at the exit. That's a nozzle. What does it do? Let's assume that you want to water your garden, and if you don't have a sprinkler, you only have a water hose. How are we going to do that? Let's say that your garden is about from here to the door. So you have a water hose on your hand. So you're going to water from here all the way to the door and then comes back multiple times. Yeah, you can do that. Or you can squeeze. the end of the hose, then I don't have to walk all the way. I can squeeze it and the water goes far away, right? That is a nozzle. So the definition of nozzle is we have a large opening at the inlet. We have a small opening at the exit. So how does it work? So this is a nozzle. We are squeezing one end of this water hose. So we have a large opening. Area is large at the inlet. So let's say inlet is number 1. A1 is large. Exit is number 2. A2 is small. Then what kind of, the conservation principle we can use? There are only 2 conservation principles that we study in thermodynamics. The first one is mass conservation. What is the mass conservation equation? M dot at the inlet is the same as M dot at the exit. Inlet is number 1, exit is number 2. M dot at the inlet, number 1, should be the same as M dot at the exit. Do you remember how to determine M dot? There are 2 different ways. Density times, to determine M dot, density times volumetric flow rate, or density times velocity, average velocity times cross-sectional area. So why don't we use this one? So to determine this M dot at the inlet, we can use the density at the inlet, velocity at the inlet, cross-sectional area at the inlet. What about at the exit? Density at the exit, velocity at the exit, cross-sectional area at the exit. Now, what is our system? When you water your garden, what is your system? Your hose, your hand, flowers, vegetables? What is your system? Water, right? Water. So what is the density of water? 1,000. What is the density of water at the end? Why? Because water is a liquid, incompressible. So this one, 1,000. This one, 1,000. So you can cancel them out. What is the area at the inlet? What is the area at the exit? What is the relation between these 2? Area at the inlet is, we have a large inlet area. We have a small exit area. So to make this equation work, what happened to the velocity? At the inlet should be low velocity. At the exit should be high velocity. Because of the mass balance, when you squeeze the end of your water hose, water velocity increases. That is nozzle. That is nozzle. This one. Then, if you have a nozzle, I know how to apply mass balance equation. After you apply mass balance equation, do you know any other equation that we studied? Yes, energy balance equation. So this is the energy balance equation we just derived 5 minutes ago. So let's study this energy balance equation for this nozzle. When you water your garden, do we heat this nozzle? No. Do we cool down? Do we provide electricity? Does it produce electricity? So there's no Q, there's no W, there's no Q, there's no W. What about at the inlet and the exit of this nozzle? So the inlet is on the ground, exit is on top of Mountain Everest. No, not that case. So there's no difference in potential energy between the inlet and the exit of the nozzle. You can neglect these 2. What about M dot? So the mass flow rate at the inlet should be the same as the mass flow rate at the exit, because you cannot create or destroy mass. Is this correct? In thermodynamics, yes. In nuclear engineering, no, right? So anyway, M dot at the inlet is the same as M dot at the exit. The mass flow rate should be the same because we only have one inlet, one exit. So you can cross them out. So what is the equation? The specific enthalpy at the inlet, number 1, plus specific kinetic energy, velocity 1 square over 2, should be the same as specific enthalpy at the exit, number 2, plus kinetic energy at the exit number 2. So this is the equation. So if you are able to determine specific enthalpy at the inlet, at the exit, we know how to do that. We studied in chapter 3 how to determine H. If it is a phase change material, we use property table. If it is pure gas, pure liquid, we use a specific heat, and then you can determine the velocity. That's how we apply energy balance equation for this nozzle system. So that's everything about the theory of this nozzle, and we are going to solve a few problems this after the full break. Okay. Thank you. Any question? No? Okay.